Hello and welcome. This is the eighth and final section in Chapter 1 for Physics 313. It's a technical section on units and significant figures. Will be an overview, but it also should help for us to frame our mind in the sense of what units do. Okay, units help us not only keep straight the data that we're working with, but they help us to get a estimate of how big or small an object is, kind of give us a sense of the order of magnitude is what we like to call it. And so formally, we start with the International System of Units and the three basic ones that we'll be working with over the next several chapters, length, mass, and time. We'll talk about mass in more detail in chapter 5, but it's still helpful to define what a kilogram is. So what is a second? Well, I mean, you go back and think about, how we would keep time, right? We would just see that the sun, kind of makes periodic, it rises every day. So you have the concept of a day. But in addition to that, it periodically rises and also sets from different locations on the horizon. And so that would kind of quantify the year. And roughly every 360 days, it would repeat the cycle. So you got the concept of 360 degrees of a circle. And then you kind of further subdivide that using ancient, I think, Babylonian system of base 6 for 60, degrees, and then 60 minutes and seconds. And so we get the concept of a second. Modern concept of a second comes from the speed of light, because it turns out, I've referred to this in another video, but it turns out that light is a deep postulate of physics, is that the speed of light is the same no matter what your frame of reference. Even a high-speed train sees the speed of light be the same as someone that's at rest. And that's an interesting topic in and of itself, and that kind of causes the definition of a second to be convolved with the definition of the meter, because the definition of a second, as you see here, it's the time required for a certain number of oscillations of a radio frequency wave that's emitted from or absorbed by cesium-133. So a certain number of wavelengths of light are absorbed by the cesium atom in 1 second. Now, where does that specific number come from? Well, that's kind of related to the meter. The SI unit of length is the meter. We abbreviate that M, not mass. And so we see the definition of a meter being, well, this is how far light travels in a second. Well, what's a second? It's the amount of wavelengths, which kind of is a unit of length, that's absorbed by an atom, given that light travels at a fixed speed. So it's kind of weird to think right now, but the modern definition of time and length are both related to the fact that the speed of light is constant. We'll talk more about that in due time. And so there are these units, these standards that are held at these places that record, okay, this is an official kilogram, by which all other, seconds or meters or kilograms are measured. SI unit of mass is the kilogram, kg. It's the only of the 7 basic units in the SI system that is defined with a metric prefix on it. Obviously, this table that you see right here, table 1.3, has important prefixes that you'll need for some of these problems. I would add to the bottom of this list, I would add, so micros -6, nanos 10 to the -9. I would add pico is 10 to the -12, and femto is -15. Those don't have symbols, just P and F. And then obviously the centimeter and the millimeter or the milligram, those are important. We usually don't use 10 to the 2 or the deci or deca prefixes. Those don't usually show up, at least not in this class. Out there in industry, they'll use whatever is most convenient, because whatever the best system of units is the one for which it's most convenient. And from a computing standpoint, you have mega, and then giga would be replaced by tera, and then petabytes or peta would be the next one. And there's yotto and hexa. I mean, you know, but these are the ones that we use primarily for our problems. Even for the next several chapters, we won't even be really using many of those. It's when we get to, well, when we get to energy and power that some of these units become important, like kilojoules, kilocalories. But be aware of those, be able to convert those. Oftentimes the conversions tend to be a headache. It's always a shame to me to count off points for a student that did everything right, but failed to make the conversion right. And obviously you can, figure out the unit conversion in about 2 seconds on your smartphone, but this is still an important tool to know. I mean, it helps you make judgment calls on assessments. For instance, 1 meter per second is about 2.25 miles per hour. That'll be really helpful when you're trying to think about what does it mean for an object to be traveling at 20 meters per second. Well, it's about 45 miles an hour. Those types of kind of critical thinking tools that you can't get just by looking up a computer. But you need to be able to work with conversions, and they have their conversion where you cancel the units. Chances are the system that you've learned is helpful for you, and this one is just presenting a formal way of doing it. So like I said, talking about assessment, automobile speeds and so forth, these assessment tricks will help you. And so that's where these conversions, like I said, are helpful. 1 meter, about 1.609 kilometers. An inch to a centimeter, that's a definition actually. Conversion between meters and inches. Typically we don't remember that one. Anyway, so those are all helpful to keep in mind when we're making kind of order of magnitude estimates. The last topic is on significant figures. Now, how many significant figures does a measurement have? Well, what do we remember from significant figures in the past? Okay, you got the decimal place. Okay, that's a good start. Obviously, any non-zero digit is significant. Okay, but so it comes down to where does the zero need to be for it to be significant? I mean, that's really the important discussion when it comes to significant figures, because all the non-zero ones are significant. So several different places where can the zero be? Well, it could be to the right or to the left of the decimal. It could also be inside or to the left or to the right of the non-zero digits. And so you need to quantify that. Obviously, if it's in between non-zero digits, it's certainly significant. If it is to the left of non-zero digits, then it's not significant. If it's to the right of the decimal place and right of non-zeros, then it's significant. But then there's this murky area where it's to the right of the non-zero objects, but to the left of the decimal. And here's the convention that the book takes. The book makes a very specific convention that might be different from your chemistry classes, but it is the thing that they will use in their significant figure calculations for your online homework. Here's the convention. If the zero digit is to the right of all the non-zero digits and to the left of the decimal, it is not counted as significant unless unless there's only one non-zero digit. If there's only one non-zero digit, then the zero immediately to the right of that is defined to be significant. So say you have a measurement of 50 meters. The book is going to define that as having two significant figures, the 5 and that 0. Now 500 meters without a decimal still only has two. It has the 5 and it has that first trailing 0. But then 500.0 meters would have 4. All those zeros would be significant. Okay, so obviously that zero, the placement of that zero and the placement of that zero relative to a decimal point if it's there, and also in relative to the non-zero digits will affect where that zero is significant or not. All this to say that don't submit an answer, whether it's even for written homework or even online, don't submit an answer with a single number in it, like 9 meters. Typically 3 digits. We don't require, specific numbers of decimal places. That will change with the context. But certainly don't keep all the trailing numbers when you do a calculation on your computer or on your calculator. Most of those are not significant. Like if you submit an answer that says, well, the car traveled, 82.738149.527 meters, well, that's what your calculator gave you, but for the most part, those trailing numbers are not significant. So just keep that in mind. We want to find kind of a balance, and this book doesn't overemphasize significant figures, but at the same time, they don't want you to think that you can only put 1 or 10 answers, okay? And so again, here we've got scientific notation, and okay, so we've got all these zeros. The zeros to the left of the 6 are all non-significant. That first trailing zero is significant. That's one example. You'll see several of these examples. And so you can go through this tactics box for significant figures. It kind of summarizes what I've said. And here's an example that you can look at in the textbook. The last topic from this section is order of magnitude estimates. These are critical when we are kind of estimating how big we want our final answers to be or what they should. You do mental comparisons with speeds, but where do you get those mental comparisons? Well, that comes from experience. And so we got estimated lengths of different scenarios. And by order of magnitudes, we mean adding another zero. So obviously, length of your arm would be kind of a baseline, length of classroom, length of football field, campus, altitude, distance of solar system, and all these order of magnitude estimates for length. We also have the same thing for mass. These are kind of interesting to see. And the book will give you typical values for these quantities that we introduce. So like a raisin evidently is 0.001 kilograms, about 1 gram. Raisin, pencil, apple. You can look at all these. Textbook, about 1 kilogram. I know our textbook is a lot bigger than that, but anyway. Okay, so these types of mental estimates keep in mind when you're comparing objects. I would say a car, what do they have? A small car, 1,000 kilograms. A medium-sized car, about 1,500 kilograms. We'll use that a lot. Pickup truck, probably close to 2,500 kilograms. So that concludes this section, and that also concludes this chapter. In chapter 2, we're going to really dive in and develop some mathematical techniques for analyzing these one-dimensional problems. It'll be primarily some algebraic models, calculus, and near the end, we'll also do some interesting non-uniform problems. Thanks for your time, and we will see you back here for chapter 2. Take care.